Welcome back, class. Today what we're going to be doing is going over piecewise linear models. Now, very similar to the last lesson you did on linear models, the only thing is we're going to piece a bunch of them together to form one large model. At the end of this lesson, you'll be able to understand what a piecewise linear model is, draw that piecewise linear model from different statements, find out what the gradient of each piece of that piecewise model is, and then extrapolate any information from the graph that you are going to draw. All right? So it's a very informative lesson. So first we're going to start with what is exactly a piecewise model. Now a piecewise model is a model made up of several straight line segments. So the straight line is the word linear, and then you have a couple straight lines here and they're connected together. Now in this case right here, the graph shows the relationship between the water used by a household, that is on your independent horizontal axis, and then your vertical dependent axis shows the cost of said water. Up to 25 kiloliters is charged at a base rate. So from 50 up here to 25 kiloliters, or 1,000 liters, is charged at a certain rate. It's a pretty low rate. And then after you hit this number, as you can see, the graph changes. It still stays a straight line, but it's a different slope. So this was a straight line, but if it continued, it would go this way. So once you get to this piece at 25, you are charged at a higher rate. Now the gradient suddenly increases because the more you spend, the more water you use. After you use a certain amount, you hit that threshold, they're going to charge you more money per liter. Now, to see this a little better, you can break this into two pieces. The first piece is your base rate. That's from 0 to 25 kiloliters. As you can see, this graph only goes up approximately $50 between that rate. Now, if you went 25 more kiloliters, the higher rate goes up over another $100. So it's twice as high, at least, is the higher rate gradient. Okay, and gradient, once again, is a fancy term for slope. All right, so as you can see, the graph is broken into two sections. Now, we're going to do an example. The cost of printing invitations on the number depends on the number of indentations printed, as shown in this piecewise linear model. So what happens is, between 0 and 100, you charge a certain amount. After you print 100 invitations, the next 100 and next bunch of invitations, you're charged at a lower amount. Okay, because the more you buy of something, the cheaper it is to make, therefore the cheaper it is for you to buy. So we're going to find each gradient. So the first gradient is AB, which is the distance from point A to point B. Now in order to find this distance, all you're going to do is find the gradient or the slope. Now gradient and slope, as we discussed in the last lesson, are the same things, and that is y2 minus y1 over x2 minus x1. It's the change in height over the change in width. Or it's rise, the amount you go up, over run, the amount you go across. So in this case, point B, point A right here is at the origin, it's at 0, 0. Point B right here is 100 over and 50 up. So y2 is 50. Minus y1 is, we should say x. y2 is 50, minus y1 is 0. So this is my x1, y1, it just means 0.1. And this is my y1, x2, y2. So my second point, my first point. 50 minus 0, 100 minus 0. All right, so the way you're going to do this is now 50 divided by 100, and then you're going to reduce that. When you reduce that, what you do is 1/2, or 0.5. All right, the book likes to do everything in decimals, so we'll just leave it in decimals because that's what they like. That is the gradient. So now do the gradient of the next one. You need to know what point C is. Point C over there. So the first 100 invitations cost $0.5 or 50 cents to print. All right, and that is per invitation, not for all of them, it's per invitation. BC, so we know point B is 150. Point C over here, though, is 280, I think, right? 280. All right, so now we're just going to say your x1, your y1, your x2, your y2. As long as the ones and the 2 stay together, you're fine. All right, so the gradient is 80 minus 50 over 200 minus 100. which is 30 over 100, which is 0.3. So what that means is between 100 and 200, and on pretty much, all the invitations after you print out the first 100 cost you 30 cents a piece to print. All right? Got it? Pretty easy stuff to make. It's just a lot of work to put everything together, but besides that, it's fairly simple. So let's continue on. Let's do B. All right. What is the cost of printing the first 60 invitations? So we can either use the graph to do this, or we can use our equation. What do you want to use? I'm going to use the graph. So 0, 20, 40, 60. So here's where 60 is. So I go up from the number of invitations to 60 to my graph, right here. And then I see how the cost is. I go over horizontally, and it is 30. So it costs $30 to print 60 invitations. All right, you can also put 60 into the gradient. 0.5 times 60 is 30. What is the cost for $74 worth of invitations to be printed? So 60, 80, 74 is about right here. I go over to my graph. It intercepts my graph right there. I go down to see the number of invitations, and that is 180 invitations. All right. Another way to solve this, so what I told you here to solve this. Another way, this is you use your gradient, which is 0.5, 50 cents of invitation, times 60, that also equals there. Another way to do this one, if you want, is I know that the first 100 invitations here cost $50 to print, right? So $50 is the first 100. So now I have $24 left. Now this $24, right, is, we said the gradient of the second one, I'm just going back to show you. The gradient of this one is 30 cents an invitation, right? So this one costs 0.50, this one is 0.30. So we paid $50 for this first one, and now we want to pay 24. So we just do our $24, right? Divided by 0.3. Oops. And when you do that, you get 80. And I know $50 was for 100 invitations. $50 for 100, so the 24 gives you an extra 80 invitations, which is 180 invitations in total. I'd stick with the graph, but it's always good to know how to do things mathematically just as well. Right? Good. All right, now you get to a problem. Problem 1. It says, consider the water cost graph. This is from our original problem. So now we're going to find the gradient of each one of these line segments. You're going to find the gradient of the base rate, and you're going to find the gradient of the higher rate. So why don't you guys go and do that? You did it? Wonderful. So, first thing we're going to do is we're going to put some points down to find our gradient, because we have to use our slope formula. A right here is 0 over 50 up. B right here is 30 over 100 up. Or is it 25 over? 25 over 100 up. Sorry, angle got me. Y and C is 5200. So, first thing we're going to do is we're going to find gradient AB. All right, your base rate. Y2 minus Y1, 100 minus 50 over 25 minus 0. X2 minus X1. 50 over 25, your base rate has a gradient of 2. So that means pretty much what you do is you're paying $2 for every kiloliter of water. Right? This one. The first 24 kiloliters of water cost $2 per liter. Oh, kiloliter. Y2, Y1. So our higher rate, 200 minus 100 over 50 minus 25. 100 divided by 25 is, well, what did I say before? 4. Is that a little bit more than twice? That was kind of right. Just trying to eyeball it. So that means that after your first 25 kiloliters, everything after that costs $4 per kiloliter. So it costs twice as much after your first 20. Find the cost of using 40 kiloliters of water. Now, there's two ways to do this. The first way, I'm going to use my graph. 40 kiloliters intersects right here. It goes over there, so 150 plus 10 is $160. Okay? A way to do this mathematically. All right, I like to show you more than one way. Mathematically, we know, what is it, the first 40? All right, so the first 25 kiloliters cost us what? What did we say, $100? All right, now, we have to go to 40, so that means we need 15 more kiloliters at $4 a kiloliter. So we take our 15 and we multiply it by 4 and we get 60 kiloliters. Guess what happens when you add these two together? 160 kiloliters. So now you're able to solve it with a graph or with just mental math. All right? C, Kelly's last water bill was $80. How much water did she use? So let's go to the cost. 50, 60, 70, 80. Still in the base rate. Bring it down. She used 15 kiloliters of water. Another way to do this if you want, very simple. Her last bill was $80, right? So we're using our base rate. She's paying $2 per kiloliter. Base rate. Her last bill was $80. She used 15. Yeah, all right. Any questions? 50. Oh yeah, because you get your first 50 free. So if you want to do this mathematically, your first 50 kiloliters is free. So you start with 80 minus 50, which is 30. And you're paying $2 per kiloliter. 30 divided by 2 is 15 kiloliters of water. All right, the reason I didn't animate this stuff is you don't need to solve it that way, but some people like to do mathematics. All right, everyone go on to problem number 2. Actually, I like to do it. I like to try to do those things, keep myself nice and fresh. All right, each month, Colin pays $2 per gigabyte for mobile phone data up to his allowance. And then he has a higher rate than he pays for any excess data. What is Colin's data allowance? All right, look at our graph. Each month he pays $2 per gigabyte. So, up to the 10, that's when it switches over for the highest excess. So at 10, you have 20. So his data allowance is, what? Is it the 10 or the 20? What's the data usage? Gigabytes. It is 10. At what rate is he charged for all this excess data? So the rate he's charged, we're going to have to find out what our gradient is. So we can use point 1020 here, and let's pick it up right there. That crosses nice. So I use this point, which is 20 over, 70 up. I'm going to use these 2 points to find my gradient, 1020 and 2070. What I do is find my pointer. y2 minus y1, 70 minus 20, over x2 minus x1, 20 minus 15. You get 50 divided by 5. 50 divided by 5 is 10. Whoa. 50 divided by 5 is not $5. It is $10. So it is $10 per gigabyte for his excess data. So what that means is for every 5 I go over, I should go 50 up. 20. Wait a second. 10, 20. 20, 70. 70 minus 20 is 50. 20 minus 10. Ah, this was 5. So that's a 10, and that's a 10. X2, X1 was really 10. I don't know why I put 15 there. So our answer really is $5 per gigabyte. See, that's why you always want to check your work. Even I make mistakes. But what I'm doing here on the sideboard is getting it so I fix it when I give you my notes online. How much does Colin need to pay for 15 gigabytes per month? So 15 gigabytes is right here. Shoot it up over, move it to the left. He has to pay $45. All right. If you want to see how that is, well, mathematically, like I said, the graph is fine. For the first 10 gigabytes, he pays $20. Okay, so $20 for 10 gigabytes, right? Now, he's doing 15. So for the next 5 gigabytes, all right, he pays $5 per gigabyte. So that's times $5 per gigabyte. 5 times 5 is 25. 25 plus 20 is 45. Okay. What total data usage will result in a bill of $60? Well, go from 60 over, corresponding to the bottom, and you get about $18, or 18 gigabytes. Right? Graphically, nice and easy. Now, you know what? I want to do this mathematically. So what I know is my total data, all right, so bill of 60, I know that once again it costs $20 for 10, right? But I'm paying 60. So for $40, I have $40 left over at $5 per gigabyte. 40 divided by 5 is 8 gigabyte. 8 plus 10 is 8. Right? Problem number 3. Graph shows the distance traveled by a cyclist on her way to work. How long did it take this cyclist to get to work? All right, well, that's where she starts. That's where she ends. What's the time? Drop it down. Took her 45 minutes. This is something you have to read straight from the graph. How far did she travel in total? Oh, look at that, perfect. Distance traveled. Go to your top point. She traveled 16 kilometers. 10, 12, 14, 16. Find the gradient of AB and then interpret your answer. So, what is the gradient of AB here? Well, this is point 0, 0. This is point, what's that, 2010? Good. So now you're going to do your slope formula. 10 minus 0 over 20 minus 0. 10 divided by 20 is 0.5. Interpret that. What does that 0.5 mean? Distance traveled kilometers. Is it 0.5 minutes per kilometer or 0.5 kilometers per minute? What do you think it is? Well, what's on top? The 10 and the 0, your y values. Your y values are the kilometers, so it's kilometers per minute. The cyclist was traveling at a rate of a half a kilometer per minute for the first 10 kilometers. Okay. She popped the tire. Can you tell where in this graph her tire was popped and how long it took her to fix that tire? Right here. Why is the green section the tire when it's popped? Because what's happening in the distance where she's fixing her tire? The distance is staying at 10 kilometers. She's not moving. She's sitting fixing her tire. You can't fix a tire while you're riding a bike. How long was she fixing the tire for? Between 20 minutes and between 30 minutes. Between 20 and 30 minutes is 10 minutes. It took her 10 minutes to fix her tire. How far had the cyclist traveled after 35 minutes? So after 35 minutes, 10, 20, 35 is right here. Go up to your graph, go over to the distance traveled, and it is 12 kilometers. All right? Problem numero 4. This graph models the speed of a car over a 20-second period. Describe the car's journey over this period. All right, let's look. The car was traveling at 10 meters per second. What? Over this time, the car was what? I don't understand that. What does that mean? Why was it traveling 10 meters per second? The reason it was traveling 10 meters per second is he went the speed 10 meters per second when he started. All right, so that's A. So the car starts at 10 meters per second. Explain this right here. What does that mean? Then the red part says He braked for 6 seconds to a complete stop. All right? How do we know he's coming to a complete stop? Well, his speed's at 0. How do we know he's braking? Well, it only took 6 seconds. You can't coast from 10 meters per second to 0 without using your brake. So he braked for 6 seconds. All right? That's good. What do you think happened between 6 and 10? What's going on in that green one? No speed. Make up something. Make your own story. Car stopped. Stopped for 5 seconds. Why is it stopped between 6 and 11 seconds? Who knows? Maybe he's at a stop sign. Right? All right. Then what does he do from C to D? Between 11 and 15 seconds. So for the next 4 seconds, he accelerates, right? He accelerates. What's that, 4 seconds? Oh, sorry, 4 seconds. Oh yeah, 11 to 15, 4 seconds. To a speed of 7 meters per second. And then what does he do for those last 5 seconds? He just goes at a steady rate of 7 meters per second. So he maintains that same 7 meters per second speed for the last 5 seconds. So this was just a statement about what this graph may be saying. Is it true? Possibly. Maybe he was driving. Now the reason you can't say, oh, you got in a car accident. Well, then this would be like a instant stop. Right? All right, the assumptions that have to be made when using this graph to model the car's speed. What are the assumptions? That your speed is constant. So you're going to accelerate, that you accelerate and you decelerate at a constant rate, which is something as new drivers, or when you guys do learn how to drive, you should do. Right? Saves gas, is better on your brakes and better on your car. You don't want to be jamming on your gas and going real quick, or slamming on your brake for the last second and go slow. Nice and smooth and steady. C, find the average speed of the car between A and B. So how do we find the average speed? Just find the gradient. What are the points? 0 over 10 up, 6 over 0 up. So, oh, sorry, this is a reasonable. That's reasonable. Most people do accelerate. So we're going to do 10 minus 0 over 2. All right? Your initial speed, your end speed. All right? Why is it over 2? 5 meters per second. Average speed of the car between A and B. Should be over 6, shouldn't it? Uh-oh. The distance traveled between A and B. I gotta look that one up. I think I messed that up. 5 meters per second times 6 seconds. All right? Which is 30 meters. All right? And then finally, the total distance traveled by the car. This one you have to solve each piece individually. It's 4B, right? 4B. That's number 4. Yes, that isn't 4B. It's 4C. 4C, number 4. 5 minutes per second. Yeah, it is 5 minutes per second. Average speed of the car between A and B. Oh, the average speed. Your initial speed is 10. Your final speed is 0. Initial minus final is 10 minus 0. And you have 2 numbers here, so you're just finding the average. All right, so average is 5. If I went right in the middle right here, 5. I don't know how that just froze. All right, total distance. Well, this one you're traveling 30 meters. Right here, in this green spot, you're not moving, so you travel 0 meters. If you go from C to D, you want the average speed here. All right, so the average speed is between 0 and 7, so it's 3.5. All right, 7 divided by 2 is 3.5, and you're going 4 meters. So 3.5, 7 minus 0 divided by 2, 3.5 times 4 is 14 meters. So this blue one, you go 14. And D to E, your average speed is 7, because it's a constant speed, and you're going 5, so 7 times 5 is 35 meters. 30 plus 0 plus 14 is 35. That gives you a total distance of 75 meters. Aha! All right. Ooh, I like this one, number 5. I just like the picture. All right, Jasper's over here. He's eating berries from a blueberry bush. Picks berries on the farm. He earns $5 per kilogram for the first 12 kilograms, and then he gets $8 for each additional kilogram. So it pays for him to work as hard as he can. Draw a graph to display this relationship of the weight and bearings he picks to his daily wage. So, draw the graph. Good. So, for the first 12 kilograms, so up to 12 kilograms, all right, up to this point, he gets $5 per kilogram. So he starts at 0, and then for every kilogram, this is 4, you go up 5. So for every 2, you go up 10. 10, 10, 10, 10, all the way until you get to 12. All right, what's 12 times 5? 60. So 12 times 5 is 60. So when he gets to his 12 kilograms, he will make $60. So you go 12, 60, you put a point, and you know this is a straight linear equation, and there you go. 4 times 5 is 20, 8 times 5 is 40, all matches up. $8 for each additional kilogram. All right, so let's go up to 20. So between 20 and 12 is 8, right? So 8 times 4, right, is, right, oh, between 12 and 16 is 4, and then times 8 is 32, so we'll go up to $32 on top of the 60. 60 plus 32 is 92. There's your graph. The reason I couldn't do 20 is this would be 8 times 8, which is 64. 60 plus 64 would be up here. Now the reason I have to add 60 to it is you already made $60. So now you're making $32 on top of that $60. So at 60, I add my 32, and that took 4 kilograms again. How much does he earn for picking 9 kilograms of berries? 9 is right here. 9 times 5 is 45, or you can use your graph right here. 45. All right. 9, right there, $45. How many kilograms of berries must he pick to earn $100 in a day? You can go up to 100, drop it down, 16, 17 kilograms. All right, if you want to do this mathematically, the first 12 kilograms you earn $60. So you need 40 more kilograms. So the next X kilogram is going to give you 40. You're making $8 a kilogram, so 40 divided by 8 is your 5 kilograms. 12 plus 5 is indeed 17. Well, that was good that I did that, right? All right, nice and easy. All right. Next one. The graph shows refrigerator services. Find the cost of the service which takes the following. Almost about halfway there. Cup of water real quick. So, to do this problem, the cost that takes 20 minutes. So let's look at a graph. Time is right here on bottom. These go up by 5, 10, 15, 20 is right there. So I go up to my graph. It corresponds with this number right here, which is $75. That's an easy one. There is no math to even show you. 45 minutes. Now there's a closed circle here and an open circle here. It does not count for the open circle, just the closed circle, which is 95 minutes. Now we're going to go the other way. Find the maximum time for a service. Now the service costs $55, so the maximum time would be right here where the closed circle is, and that would be 15 minutes. 115. Now watch what happens here. 115 goes right there. Drop it down, and you drop it down to 60 minutes, so an hour. Now, getting a little more advanced. Say there's an 80-minute service. Look what happens. At 80 minutes, what do you think the cost would be? Well, it's $115, all right? You think it's 115? Or 60, 80. 80's right here. So it was $115 right here. You think that's what it is? No. You're going to add 20 extra dollars, because that's from 60 to 75. So what happens is, From 0 to 15, 55. From 15 to 30, 75. From 30 to 45, 95. What you're doing is you're pretty much jumping $20 each time you go up 15 minutes. So from 45 minutes to 60 minutes, it was 115, but we wanted 80. So then you go up $20 more. So you go up to 135, and that's from 60 minutes to 75 minutes. That's no good. So we have to go up another $20 from 75 to 90 minutes. That is 115 plus 20 plus 20, which is $155. All right, because every 15 minutes you go up $20. Got it? And it won't be on the graph, but that's fine. All right, problem number 7. The way this one works, the cost of sending a parcel overseas depends on the weight of the parcel. Draw a graph to display the information given the table and the weight up to 5 kilograms. All right, so what you're doing here is you are going to continue on with your answer. All right, now the way this works is very simple. We're going to draw the graph. Now the way to draw the graph is up to 500 grams, it costs $13. All right, so weight in kilograms. 500 grams is half a kilogram. So 0 to 5, it costs $13. So I'm going to put a little graph right there. Okay? You don't pay for anything. If it's $0, you don't pay any money. But then anything above that, you're going to pay up to 5 kilograms. Up to half a kilogram, you pay 13. Now over this much, so that means not included, just over this, and up to a kilogram is 23. So from here to here is 23, put another little mark. Over 1 kilogram and up to 2 kilograms is 32. So now we're going to go from 1 to 2. 32. But not included because it says over. Over 2 and up to 3 is 40. Now, this one may confuse you. An extra kilogram or part thereof is $5. So what that means is, what happens here is, every kilogram afterwards, you add an extra 5. So from 3 to 4, you pay 5. That should be an open circle. 5, 5, and 5. All right? Find the cost of sending the weight. 750 kilograms. Between these two, $23. 1.6 kilograms. Between these two, 32 kilograms. 3.4 kilograms. Up. An extra kilogram thereof. So 40 plus 5 is $45. Heather has 1.7 kilogram parcel and 2.8 kilogram parcel to send to her mother. How much money will she save by sending these parcels together as one package? All right, so let's start. 1.7 kilogram costs $32. 2.8 is $40. Together they cost $72. Say she sent them together. 1.7 plus 2.8 is 4.5 kilograms. All right? So 3 to 4 is 45, and then if you add 5 more, that's 50. So that would be $40 plus 5 would be $50. How'd I get? That's not right. 40 plus 5, and that's from 3 to 4 plus 5, so this is 50. 72 minus 50 is, she would save $17. I was doing so good too with my answers without making mistakes. All right. Oh, and I got 17 there. Magically got the right answer, even though my math was wrong. 27. Not 27, it should be 17. 50, wait, 72 minus 50 should be 22. I should say 22. I was off everywhere. Should say 72 minus 50 is 22. All right. Oh, see, everyone makes mistakes. 7. All right. 8. Swimmer. Swimming A, 200-meter medley. Swims all 4 strokes, butterfly, backstroke. Breaststroke, freestyle, 1 race. All right. Lowers time for each 500-meter leg is shown in the table. Sketch the difference distance time graph in the model and her position during the race. So watch what you have to do here. So she swims the butterfly for 20.8 seconds. All right. So her times for each 50 meters. So it takes her 50 meters, the first 50 meters to swim this much. This is your distance. So up to 50 meters, it takes her 28.2 seconds. All right. Now the next 50 meters, she's swimming the backstroke. All right. So up to 100, she's swimming this. So we're going to take our numbers and we're going to add them together. You get 57.48. So to get up to here, 57.48. Now, she goes 33.91 seconds to get to the next 150. Add that to this number, 91.397. So she's slowing down a little bit. And then finally, her last one is her freestyle. You take that and you add it there to get to 200, and then connect. All right? The key is that you're adding a new number to each one. So B, any assumptions did you make when completing this graph? Of course you made an assumption. You assumed that she was swimming the same rate each 50-mile leg. You assumed that she started and ended at the same rate. Otherwise, you would have like a bunch of, like an exponential graph, which is more realistic, but we're just doing estimations. Use the graph to estimate how long has she swum, I didn't even know that was a word, after 1 minute. Well, 1 minute is 60 seconds. So we can go, okay, she swam a little bit more than 100 meters. Using the graph, I'm going to estimate it's about 104. Because this is 100, this is 125. This is about a little less than a fifth the way between the two. And there you go. Problem number 8, all finished. Now, we're going to change things up a little. We're going to go into example number 3. This table shows the income tax rates in the United Kingdom in 2018. All right, now, why is this important? Well, it's not really important except for to explain what we're going to explain. If you made up to 11,850 pounds, you didn't have to pay any taxes, nil. If you made between this much money, you paid 20 pounds for each pound above this amount. So you didn't pay anything for your first 11,850. Every dollar above that, you paid 20 pounds for it. All right? If you made this much, you paid 6,900 pounds, which is pretty much 0.2 times the difference in between these two numbers, plus 40 cents for each pound above this. If you made over 150 pounds, you made this much money, which is the difference between this times 40, plus 45 cents for each pound. So what they do is, the more money you make, the more taxes, the higher your tax rate is. In the United States, what they used to do is if you made like, I'm just going to make, I don't know if this is even close, say you made up to $50,000 a year, your tax rate like 10%. If you made like $1 million a year, your tax rate was like 60% of your money. So the more money you make, the more they take from you, higher percentage. And those numbers aren't true, I'm just giving you an example. So we're going to draw a graph based on this. So up to 11,850, don't make anything. So from 0 to about 11,850, nil. You don't make any money. You don't pay any money for taxes. That's nice. Up to 46,350, you make about 20 cents for each one. Now that goes up to 46,350, 6,900. All right. So, from this number to 150,000, you're paying 40 cents for each dollar. So 40 cents times the difference between these two is where the 48,360 comes from. And then you're just paying pretty much 45 cents. You have a gradient of 45 afterwards, and it just goes up. As you can see, the more money you make, the steeper your curve gets. Find the amount of tax paid by a person who earns $50,000 a year. All right, well, let's look at this. If you earn $50,000 a year, you're in this bracket. So you pay 6,900 pounds plus 40 cents for every amount over that. So you do 50,000 minus 46,350 plus, what do you get? Oh, 50,000 minus this amount is 3,650. So the tax paid is going to be your 6,900, your original amount, plus 40 cents times this amount, which is the difference between 50,000 and the amount you made. The way the book does it is they set it up algebraically, which I don't like. But PEM does this plus this times this, multiply first, then add 6,900, and that means you paid 8,360 pounds. Right? That's not terrible. That's under 20%, less than what we all paid. All right, let's do another one. Use this table in example 3. We're going to answer a bunch of problems with this. So, first one, the minimum wage in the United Kingdom is 7.83 pounds per hour. Find the annual tax paid by a person working on minimum wage for 36 hours per week for 50 weeks out of the year. All right, so this many hours, amount they make times the hours per week times the weeks per year is going to tell us how much they're going to make. All right, so this times this times this, they make $14,094 per year. All right. That is this bracket right here. So they're going to pay 20.2 pounds for every dollar or pound above 11.80. So I'm going to do this minus 11.80 is 2,244, right? This plus this equals this. All I'm doing is subtracting the two. This times your 20, and my rate would be 448.80 pounds. That's it. Easy. B. Harold's a train driver. Train driver Harold. He pays $53,172 per year. What tax rate? So let's look. Falls in this category. All right, so this is what he's paying. Subtract the two differences. All right, 53,172 is this number plus this number. You just subtract the two to get it. You're going to take this number, multiply it by 0.4, and add it to 6,900. And the taxes he pays are 9,628.80 pounds. Find his salary after income tax has been deducted. So how much does he actually make? Well, you take this away. You take his initial salary, 53,172. You subtract the amount of taxes he had to pay, and his actual salary is 43,543.20 pounds. Right? Now we're moving. Next one. Now we got the Prime Minister. Ooh, big money maker here. He was making 970 pounds. 907 pounds. So how much did he pay? He's in this big tax bracket. So let's see. 150 plus 3,907 gives us the salary, right? 3,907 times 0.45 plus 48,360. He paid 50,118.15 pounds. So he almost paid a third of his salary. What percentage did he pay? Well, to find the percentage, there we go. This number that he paid over his actual salary times 100 and that's 0.326 or 32.6%. So like I said, he paid almost a third of his salary in taxes. And the first guy paid less than a fifth, less than 20%. New one, new graph here. For 2018-2019, government set the income tax. Now we're going to Australia. All right? Slightly different. Draw a graph. So now what we're going to do first is we're going to draw the graph, and then we're going to answer a bunch of questions based on the graph. By bunch, I mean two. So first thing, up to 18.2, didn't pay anything. Up to 37,000, 37,300, 3,572. All right. These are the points: 0, 0, 18,200, 0. Right, because you don't go up yet. Between here and here, you're 0. And then when you go up to 37,001, you're going just a little bit higher. That's going to be your initial amount. All right. So then when you go up to 90,001, you got your 20,000. All right. Then you're going to go up to your 180,001. You got your 54,000. And then everything after this has a slope, a gradient of 0.45, and it just pretty much shoots up. I did it up to 20,000 just to get a number. I jumped up that much. All right, I went from 180 to. It just gave me a good number to plot and do my point with. All right. And you can actually go through here and draw a line. So, where am I at? Feel good? That was A. B, draw a graph showing the rate against incomes between 0 and 200,000. So the first graph was, taxes paid. So now you're doing the tax rate against the incomes. Okay, so from 0 to 1,800, that's your tax rate. This tax rate is 0.19, 19 cents. The next tax rate is 0.325. Between these two. This tax rate, 0.37, so you can see how they go up based on the things. Now if I actually took these two graphs and put them next to each other, you can see this is where the gradients go up. So the largest tax rate is for the middle people. Calculate the income tax, so what are the actual income tax? So I'm making 28,000, right here. What will the tax be? 0.19 times 28,000 minus 1820, it would be 1,862. 48,000 is right here. All right, so you got 3,572. 48,000 minus 37,000 times 0.325. That gives you $7,244.50. All right. 96, that's in this green one. So you're going to do $20,787 plus 0.37 times the difference between 96,150 and 9,000. Multiply it by 0.37, then add 20,787 to the answer. And when you do that, you get $23,062. $23,062.50. All right. Now, that pretty much completes all the exercises we had. I'm going to throw in a quick little activity here for you. What it says is it's the nonlinear, so it's not linear anymore, piecewise equation. The models we have studied in the previous section are built out of straight line segments. In the world around us, though, there's really no situations that use straight lines. All right. There are many situations where piecewise models are involved, but then you have curves on top of that. It's very useful to logically consider each process and then how each of the curves in the model result to a physical situation. So we're not going to get too much into math, though. We're just going to try to figure out which one is the correct answer. So let me read this to you, and then you guys are going to figure it out. When a kettle is another word for a pot, is turned on, like you're making coffee or water pot.
You have to leave the building by 4 o'clock.
The energy added to the water
You must leave the building by 4 o'clock.
causes the temperature to rise. When the water is in liquid phase, the rise is fairly constant. As the water approaches boiling though, large amounts of energy are needed to convert that liquid into a water vapor. So the energy is lost as bubbles. They are formed, the bubbles forms, and they burst. As the kettle is switched off, the water starts to cool back to the temperature of the room around it. The rate at which the temperature falls is based on the difference in the temperature of the room. And so it initially falls rapidly, then it slows down over time, right? Which the following piecewise graph accurately describes what I just told you. Read this again and figure it out, all right? Now, quick little explanation. Kettles turned on, the energy added to the water causes the temperature to rise. So initially the temperature rises. Well, they all rise here. All right, the rise is fairly constant. All right, so it kind of rises at a constant rate. These are all kind of constant. All right, I don't know about this first one, but the other ones are fairly constant. After the kettle is switched off, the water starts to cool back to the temperature of the room around it. All right, so it cools fairly rapidly around. So I don't know about this A. This A doesn't look too good, but one of these may be good. Initially, it falls rapidly, really fast, and then it slows down over time. So based on that information, it's going to fall rapidly and then smooth. I would go with this one. It rises at a constant rate, falls rapidly, and then generally over time. The difference here is it's at the same temperature for a while, which really doesn't happen. Right? Because as soon as that thing's boiling, you turn it off and it cools immediately. There you go. Let's look at the other one. When a skydiver jumps out of a plane, their descent to the ground has several phases. Initially, it's a smooth curve under constant gravity. All right, however, as the speed increases, they face more and more air resistance. As a consequence, they approach something called terminal velocity. That means you can't go any faster. All right, eventually, the skydiver activates their parachute, and it causes a rapidly decrease in speed. Thank God. All right, they will then slowly descend to the ground. Which of the following piecewise graphs describe it? So let's break down this thing. It is a smooth curve under constant gravity. So it goes, nice little curve. Not a curve, it's bad. So one of these, smooth curve. As the speed of the skydiver increases, they face more and more air resistance. They approach something called constant velocity. So you're going down pretty much at the same speed until you hit a acceleration. So you're going to go constant speed. Parachute opens, and then they go down slowly. So it's going to be either one of these two. Which one do you think it is? If you said the third one, you are correct. The difference between these two is this really isn't as constant as the velocity here. And what happens here is when you jump out of a plane, you go down fast. You're not going to float in the air for a little bit at the same speed you would do as a parachute. You go down pretty quickly. All right? Not really to that one. All right, and guess what? That's it. That was a fail. So hopefully today you learned about piecewise linear models, how to graph them, how to read the graphs of them, how to read tables that introduce them, how to do all that other stuff. All right, so now you're masters of regular linear models, piecewise linear models, and now we just have to create some more stuff. All right, so until the next time, see you guys later.